So, what are the properties that we have seen? It was memory property and invertibility. Let's continue with another property. It's causality. So we must decide whether the system is causal or non-causal. Anybody who speaks English will know the word because, right? Because, we know. Causal, causality, etc. is like saying because. Because of the input, the output must appear, in other words. That is the definition of causality. For example, y of n is equal to summation k from minus infinity to n, x of k, the famous accumulator. This is a causal system. Why? Because it depends on the present and the past samples only. A non-causal system, on the other hand, could be like this, x of n plus 1 minus plus x of n minus 1. Why is it non-causal? Because it doesn't depend on the past data. It also depends on one future data at least. This is a future data which didn't come yet. Such systems are not physically implementable if this axis, the free variable of the function, is time. Because in time you cannot go to the future. That's not possible. So you cannot physically implement those non-causal systems. But as we have already discussed before, it's not mine. Anyway, okay. I didn't open the door anyway. Such non-causal signals or systems are physically implementable if the free variable is not time but something else. For example, the coordinates of the image, because we know that this is a coordinate of an image, a digital image, let's say, and one neighboring pixel is also a sample of the image, another pixel, and they are simultaneously available. So if this coordinate is n, then at this point n is equal to 5, and at this point n is equal to 6, let's say. In order to determine the image processing output, you can both at the position of 5, the output pixel at position 5, suppose it's a filtering. We filter and the output at position 5 may depend on the input at 6. It doesn't mean that it's a future time, it's just one neighboring pixel. And that means such a thing is possible then. So physical possibility is only available for non-causal systems when the free variable is not time. If it is time, just forget about it. We don't have the future data during the execution of the system. For example, another example. This one I will ask you. This is an averaging filter. We want to average from minus m to plus m neighbors of a discrete time sequence like this. 1 over 2m plus 1 is for the averaging, and the summation is from minus m to m x of n minus k. This is y of n. This is the system. Is this system causal or not? Is the question then. It's non-causal because for some values of m, the position is here, n minus m to the past and n plus m to the future will have to be averaged. We are averaging all these values to discover the value of this thing at the output. So this is non-causal because of those future parts. Another question that sometimes confuses people are like this. Y of n is equal to x of minus n. Is it causal or non-causal? It looks like causal, but only if you think this n to be positive. For positive indexes, y of 5 is equal to x of minus 5, which is a past data. But how about y of minus 6? For that, you need to know x of 6, which is future, as opposed to the current sample value of time index of minus 6 at the output. So for half of the signals, it is becoming non-causal, which makes the whole input-output system to be non-causal. You must say it like that. Okay, so this is non-causal. Do we have examples about that? Let's see. Well, they are just trivial examples. Let's just list down a few of them. For example, y of t is equal to x square of t minus 1. Is it causal or not? Yes, it is. It is causal. It only depends on the past input. Be careful about the notation that I use. From calculus, you should be using it this way as well. What this really means is x of t minus 1 square. Right? They are the same things. This one is the same as that. Just the sample-wise square of the value. So instead of writing it like this, I prefer to write it like this. It's not the square of an individual entity called x. X is a function, x of t is a function. I'm taking the whole square by this kind of a notation. Okay? Let me remind you about that. But of course, y of t is equal to x of t plus 1 is non-causal. How about this? Y of n is equal to 1 over 2 to the power n plus 1 x cubed of n minus 1. Now this one is a little bit tricky. Please think a bit about this before giving me the answer. Is it causal or not? This is a bit ambiguous. What would you say? Causal, non-causal? Causal. I would say this is causal. Because the sample requirement for the output is the past input, x of n minus 1, the cube of it. There is an n plus 1 here appearing, but that is only the value of n that we use. It's not x of n that we use over there. Okay? So this is, causal. Although it looks a bit non-causal. Okay. The next property we may talk about is stability. You know the meaning of stable, right? Stable means its output doesn't diverge. That's what a stable system means. So stability is a requirement for some systems, and it's a property in general. And this is usually critical. Checking the stability of a system is critical for control systems, for example. Because you want to contain and control something at the output, and you don't want the output to blow away. The definition of stability that we will use is bounded input, bounded output stability, which says that as long as the input you apply has finite values, bounded, then the output is expected to be bounded as well, not go to infinity. For this, Unfortunately, we don't have the tools again, just like the case of invertibility. We don't know how to invert systems yet to check whether it is invertible or not. We only have some examples. For this thing, we must do something similar. We must stick to the definition of examples. Okay, we don't have the necessary tools to analyze a bounded input, bounded output, and there's an abbreviation for that. It's BIBO. BIBO stable or BIBO unstable thing. So let's think of the accumulator again as an example. Okay, from minus infinity to n, x of n. Is this a BIBO stable or BIBO unstable system? It is an unstable system, because if you apply a constant input, let's say 1, all ones, then as n goes to infinity, the accumulation will grow indefinitely. The output grows without bound. But of course, if the input is a finite duration, finite value input, then the output will have some finite value. But the bounded input doesn't mean that it is bounded in time. It means that only the values are bounded and it may extend to infinity. Even in that case, for an infinitely long sequence, again, this is x of k. I'm constantly doing this mistake. The output should still be contained within some value, no matter how long a sequence it may be. It may be an infinite extent sequence. So you must check such things for bounded input, bounded output stability. All right. The tools to detect stability will be available to you soon, in a few hours. So let's stop this thing at this point, because after seeing a few more properties, we will jump into a specific class of systems, and with the approximation or assumption of those two specific properties, it will be easier to analyze stability. And it will start by time invariance. The answer to this could either be the system is time invariant, or it could be time varying. It's like checking whether the system is behaving the same throughout the whole time. Does it change at different times? Is the behavior of the system changing at different times? Or is it behaving always the same? No matter where you apply the input, the output will be this. So if you apply the input like 5 minutes ago, then the output will be the same 5 minutes ago. So the input, if the input is shifted, then the output must be shifted without any further alterations. This is the system, and the output is y of t. This is an example in this continuous time. Discrete time examples will be similar. X of t minus t0. So it's a shift by an amount of t0. T0 could be positive or negative. It doesn't change anything. For all t0, we must have this output, y of t minus t0, and there shouldn't be any further alterations, like in a different scale or anything else. Okay, so this is time invariance that we must check. The example, which is a counter example, so the system that I will write is a time varying system. It will be in discrete time. Y of n is equal to n times x of n. This is an input-output relation which explains the system. Is this kind of a system time invariant or time varying. When x of n is applied, y of n is obtained. You must answer this question: do we get y of n minus n0 if input is x of n minus n0? Okay. If the input is x of n minus n0, what is output? Let's call it y1 of n is equal to n times x of n minus n0 with that input. Now, is it equal to y of n minus n0? Is this new y1 of n with this input the same as y of n minus n0? What is y of n minus n0? From the definition, y of n is equal to n times x of n. Y of n minus n0 is n minus n0 times x of n minus n0. And the answer is no. They are not the same. N times x of n minus n0 is not the same as n minus n0 times x of n minus n0. They are different. One has a multiplication of n, the other one has a multiplication of n minus n0. Usually, as a rule, you may always check it like this. If there is a time variable out of the time index of the function, if n or t appears outside x, in other words, then you may suspect that it is not time invariant. It is time varying then, because time will be out of it. Since time is at the output, if time changes, the output will also change. The behavior of the system depends on time. Okay? Usually that's the case. Another example. Y of t is equal to x square of t. Is this time invariant or time varying? It's taking the square of the input as the output. If we apply x of t minus t0, then y1 of t, the new output, will be equal to x square of t minus t0, which is x of t minus t0's square. Is this equal to y of t minus t0? Y of t minus t0 is x square of t minus t0, and you say yes, they are equal. So this is time invariant. This time invariance is one of the two most important properties that you must keep in mind for this course. Stability, memory, causality, those things are not very critical as a check. But throughout this course, you will have to check whether a system is time invariant or not. So remember these things. It's among the most important. The other most important one is linearity. Is it linear or nonlinear system? Linearity is the answer to this check. X of t goes into a system, and let's say x1 of t goes into a system and y1 of t goes out. This is the input-output relation of your system. And the same system has also x2 of t going into S and depending on the new signal, a new output goes out. You also observe this. Now, this system must make must satisfy the two observations. If you scale the input, the output must be scaled with the same scale. So if you input twice the signal that you previously entered, x of t provides y of t. A times x of t must provide a times y of t. This is rule number one. The other rule, when you combine the two inputs, x1 of t and x2 of t, the output of the system must also be combined in exactly the same way. y1 of t plus y2 of t. Right? And they are usually combined, these two conditions are usually combined in a single condition like this: a times x1 of t plus b times x2 of t, when they go into a system, must produce a times y1 of t plus b times y2 of t. This is linearity. A linear system is independent from combinations of inputs. The outputs will also be combined, and scaling of the inputs. If the input is scaled, the output is scaled in exactly the same way. That is linearity. For this, let's see a few examples. And let me remind that, as I said, time invariance and linearity are the two important things, two most important properties for systems throughout this course. We will have a specific and dedicated name which satisfies these two conditions. We will check whether the system is linear and time invariant or not. If it is both linear and time invariant, that's a very nice system. Then we have the tools to analyze them. For example, is this system linear or not? It looks very linear because it's a line equation. Y is equal to 2x plus 3. It's a line equation. What a pity, it's non-linear system. The line equations is not enough for us. We want the line to pass through the origin as well for a linear system. This one doesn't pass through the origin because of this plus 3. Why am I saying this? If the new input is equal to, let's say, 2 times x of n, we are scaling the input. What is the output? It is 2 times x n plus 3, which is 4xn plus 3. Now, is this equal to 2 times y of n? Because if the input is twice, we want the output to be twice as well. What is 2 times y of n? Y of n was this. Twice of it is 4xn plus 6. And the answer is no, they are not the same. One of them is 4xn plus 3. The other one is 4xn plus 6. As you see, if the input is twice, the output is not twice. They are different values. So it makes this system of input-output relation to be a non-linear system. It's not a linear system. So this example gives you a hint, a first check, if you wish, whether the system is linear or not, just look at the zero input case. If the input is 0, is the output 0? No, it's not, because the output is 3 if the input is 0. So the line doesn't pass through the origin. It must pass through the origin. If it doesn't, then immediately say that it's nonlinear. But that's not enough. That's not the only thing that you must check. For example, y of n is equal to x square of n. It is quadratic, of course, and it's not a line. Therefore, this is nonlinear. And in fact, indeed, it is nonlinear. Because, again, if you apply a new signal which is twice of x of n, let's say, I'm just writing a counterexample to show that it's not linear. If the input is twice of x of n, then the output is, the new output y1 of n is the square of 2x of n, which makes 4x square of n. Now, is it the same as, if the input is twice, the output must also be twice? Twice of y of n, which is twice of x square of n? No, it's not, because this one is 4 times x square of n, this one is twice x square of n. These are the easy example cases, but they are not very much practical. The practical examples that we will have are the difference and the differential equations. And for such equations, it's quite difficult to make these observations. So you must know whether these are linear or not before answering a question. So just learn it that way. Y of n minus, for example, 2y of n minus 1 is equal to 3x of n plus 1 over 2x of n minus 1. This is a difference equation. It's just like a differential equation. Another example could be 2d squared by dt squared y of t minus d by dt y of t plus 2y of t is equal to d by dt x of t plus 2x of t. This is a differential equation. This is a difference equation. If there is no constant term in either side of the difference or differential equations, like plus 3 or anything, if there is no such thing, then these are the proper ones that you may consider to be linear. So any system which has this kind of an input-output relation will be a linear system. This one will also be a linear system. It's also difficult to analyze the time invariance or time varying properties. They are also time invariant. So difference equations and differential equations in these forms without any constant terms in either side are linear and time invariant. Unfortunately, we have the examples to easily show you linearity and time invariance, like this one. But these are very useless systems. The systems that we will more commonly use will be difference or differential equation forms. And they will be linear and time invariant, which is a property by itself. So let's give a name to that property. And that property name is linear and time invariant systems. The abbreviation is LTI, and it means linear and time invariant. There was an exam question in some year which had one verbal question. That was the only verbal question that I have ever asked. And The question was, what does LTI stand for in our course? Write it. There were several awkward answers like literature, it means. Or I don't even remember, very strange answers. It corresponds to linear and time invariant. Okay? And that's a very fundamental class of systems. We will always deal with LTI systems from now on. If the system is not LTI, then forget about it. We're not going to learn the tools to process those systems in this course. In this course, we are dealing with LTI systems only. I have already told you that difference equations and differential equations always form an LTI system. So these differential equations can be obtained by circuits, RLC circuits, for example. So it's very suitable for electrical engineers, and it's also very suitable for mechanical engineers as well. Difference equations are usually suitable for digital processing. So digital signal processing people will be dealing with the linearity and time invariance of such things. If it is nonlinear or if it is time varying, then it's a research topic usually. You shouldn't expect a problem like that. Or, well, I should put it in a different way. You should expect problems like that. That would be a problem then. If the system is nonlinear or if the system is time varying, then that's a different problem which requires further analysis beyond the knowledge of signals and systems. That's graduate level, master's and PhD level elaboration. Okay, we're not going into the details of that, but it may be the case that when you go to the field, work as an engineer, the problems that you encounter may be nonlinear. Then you will at least know that the tools that you learn here will not be available to you. Don't rely on them. You must immediately make this kind of an observation then. So LTI systems, linear and time invariant systems, are a very dedicated and specific class of systems. And for them, we have, okay, let's forget about those things. We have one tool. If the system is LTI, in that case, one specific input-output relation is sufficient. And that one input-output relation is a very specific input called impulse that we have seen before, right? We know what an impulse is. Let's start with the discrete time because it's easier to explain in discrete time. If you understand this description, then you may extend or generalize to continuous time systems. Like summations will be converted to integrals, things like that. So delta n is what? It's a single sample at the position of 0. It goes into your system and you make an observation. If it's an LTI system, you can do this. And this is enough to completely explain everything. And the observation is called the impulse response. Why? Because it's the response of the system to the impulse. So the names are very meaningful, okay? Don't think of the phrase impulse response as something magical or something Chinese or anything. It's very English. Impulse response. The response of the system to an impulse input. You apply the impulse, you make an observation. Suppose something like this. It looks like the system is being perturbed by this impulse and then it decays, sort of, right? This example I'm giving you is something like that. Of course, this is something that you have to measure. For any system or any different system, this is different. Now, the question you have to ask me is this enough to completely describe the system? When I know h of n, in other words, do I know the system completely? What do we mean by knowing the system completely? Knowing the system completely is this. Instead of an impulse, if I input another signal, any other signal, will I be able to evaluate the output? Is it enough? And the answer for LTI systems is a big yes, it's enough. As a matter of fact, that's why for LTI systems, they don't indicate a system with an S, but they indicate the system with an H. And this H is nothing but H of n, the impulse response. An impulse response description of this linear and time invariant system is enough for us to determine any kind of output to any kind of input. All the outputs to any kind of inputs. Why?